my name is Liam Gleason, and this is Lab 5 for Physics 2211 at Georgia Tech. Now, just to overview what we will be going through. First, introduction, then we will be covering the physics fundamentals, followed by the experiment setup, then the tracker, then the glow script code, comparing the glow script code to the tracker model, and then some conclusion questions. The purpose of this experiment is to analyze the motion of a falling Slinky and determine the impact of its surroundings on its fall. During this experiment, we will also see how the bottom of the Slinky stays in place when it is dropped. The system is the Slinky, the surroundings is the earth and air, and the assumptions we are making is that no other forces are acting on the Slinky, and the Slinky starts from rest. Now, on the fundamental formulas involved, first we have the Slinky force, which acts as a tension force in the opposite direction as gravity. We also have the drag force, which acts in the opposite direction of gravity, and that is found by the formula the negative magnitude of velocity squared times the unit vector of velocity. Newton's second law is also involved, which states an object in motion will stay in motion until influenced by a force from its surroundings. We've been using it all semester. It is the change in momentum over the change in time. And in this case, our F net is equal to the force of the Slinky plus the force of gravity plus the force of drag. I will use Tracker to track the movement of the bottom of the spring in the video. I will record the data from the video, starting from the bottom of the Slinky that started from rest to the time it fell. We will then create a computational model of the spring movement using fundamental physics principles and the known times. Then we will compare the computational model with our tracker model, then determine the reasons for differences between the two. Here's my tracker analysis video right here. As you can see, it starts from rest, the old man drops it, and the bottom remains in place until the Slinky is fully compressed, and now the entire system falls. Alright. Now tracker analysis. The initial mass was 0.25 kilograms. We assumed the man holding the Slinky was 1.75 meters tall. The initial Y position was negative 1.38 times 10 to the negative third meters, and it stays at this position from 0 to 5 seconds. And then the bottom of the spring changes position from 5 to 8 seconds, and the final Y position was negative 5.16 10 to the negative 1 meter. Now here you can see our glow strip code. The initial masses is the same. We have the same position vector, and as you can see, velocity starts at 0 because it starts from rest. And then over here you can see our calculation loop to update the position, velocity update formula, position update formula. This is where we update our delta t. We advance the clock, and as you can see here, this was the output. Now, there is a discrepancy between the experiment and the computational model. As you can see, the computational model has a more negative slope than the experiment, and the changes are more volatile. Possible errors for this could include the drag force being off, the tracker data could be off, and also not all forces were included. We assumed the height of the person, this could have been off, and the amounts of the starting time are the same for both lines, but as you can see, they begin to differ when the Slinky starts to drop. And finally, we have some what-if questions. Does the bottom of your model Slinky stay stationary just like in the video? And the answer is yes. If you saw the chart, you will see it remains constant or unchanged in the beginning. If I go back here, you can see that is this line right here. You can see the orange and the blue both remain constant in the beginning. Why do you think the Slinky temporarily remained stationary? Well, this is because at the bottom of the Slinky, the forces in the Y direction, gravity, and the Slinky force completely cancel out. The magnitude of the tension force pulling the Slinky up and the magnitude of the force of gravity are equal and opposite in direction. Therefore, there is no change to the position of the bottom of the Slinky in the first about 5 seconds. And that's all. Thank you guys.